Suppose that I have a hydrocarbon CXHY. So x and y here are just integers. So for example, in the case of ethene, you'd have x equals 2, y equals 4. So, just substituting this in, you get C2H4. So I just use x and y to denote the number of carbon atoms and hydrogen atoms inside this hydrocarbon. Simple. So let's consider the case where we burn this hydrocarbon. So if you may recall, if you burn a hydrocarbon, your combustion products are just going to be carbon dioxide and water. Now, so if you burn your hydrocarbon, you get these. And this is assuming that this is incomplete combustion. Of course, if it's incomplete, then you'd get carbon monoxide and all of these other things, right? But we'll just focus on the case of complete combustion. So if I completely combust this hydrocarbon, I will write N oxygens. So maybe that's a bad way of writing it. Let's say lowercase n, N oxygens, and then I will get, well, for complete combustion, I want X CO2 molecules, and I want Y over 2 hydrogen molecules, right? Because, a water molecule contains 2 hydrogens, as you can see here. So if I want to turn all of these hydrogens, if I want to attach them to a water molecule, I'm going to need to use 2 hydrogens per water molecule. So that's why in complete combustion, you're going to get Y over 2 oxygens. And the same reasoning goes with why I have X carbon dioxide molecules. If you remember, your carbon dioxide molecule looks like this. So if I want to trap all of these carbon atoms in this molecule, I'm going to need to use all of them, meaning X, because 1 per molecule. So then what happens is, we'll figure out N first, but I have X CO2 plus Y over 2 H2O. So I don't know what N is, but I know that in complete combustion, no matter what, as long as this combustion process is complete, I will get this out. That's just the definition. Like the hydrogens get turned into water, and the carbons get turned into carbon dioxide. All of them, no exceptions. So let's solve for N, right? Because the number of atoms on the left-hand side need to equal the number of atoms on the right-hand side. So let's have a look at this. On the right-hand side, how many oxygens do I have? I have X carbon dioxide molecules. Each carbon dioxide molecule has 2 oxygen atoms. So the total number of oxygen atoms from the X CO2 molecules that I produce is just 2X. And if we look at this, the total number of oxygen molecules that I produce here is Y over 2, whatever Y happens to be. And because, look at the structural diagram for the water molecule. I've got 1 oxygen atom per water molecule, and I've got Y over 2 water molecules, whatever Y over 2 may happen to be. It could be 6, 5, whatever. So I've got Y over 2, and I know that each water molecule contains 1 atom of oxygen. So I've definitely got to have Y over 2 oxygen atoms, certainly. So this implies that the total number of oxygen atoms, let's write this down, I'll use N to denote the number of oxygen atoms. This is not so good notation, but whatever. On the right-hand side is just 2X plus Y over 2. Now look here. The number of oxygen atoms, this is an oxygen molecule, so it's like this, right? So that means this is just 2N oxygen atoms. So the number of oxygen atoms on the left-hand side is just 2N. I've got to set these equal in order for the equation to be balanced. So it follows that if I set this guy and this guy to be equal, I just substitute what I have here and here, then I just get 2N equals 2X plus Y over 2. And then I want to solve for n. This is my unknown. This is not my unknown. This is what I'm given with. So I just solve for n. And if I divide by 2, I just get x plus y over 4. So there we go. We've derived the general equation for the complete combustion of a hydrocarbon. It's this. CxHy plus, I just substitute n here, x plus y over 4 oxygens gets into xCO2 plus y over 2 H2O, which is exactly what you see in your lecture notes. Now, it's important to note that the states depend on what the temperature is. If your temperature, I'll use T to denote temperature, is less than 100 degrees Celsius, then you would have essentially this CxHy in gas. This guy will always be gaseous. X plus y over 4 oxygens in gas. And then the combustion products remain the same. Doesn't matter. X carbon dioxides in gas plus y over 2 waters. And if it's less than 100 degrees Celsius, the boiling point of water is less than 100 degrees Celsius. So this guy's going to be a liquid. And, well, if T is greater than 100 degrees Celsius, basically what you do, you just take this entire equation. It remains the same. The combustion products do not change. That's what's important. And then all you need to do is just flip the liquid to a gas, because water would have turned into a vapor. So just something to keep in mind. But the main purpose of this, I suppose, tutorial was just to show you how this equation was derived. The most important thing to note is that x and y are what you're given with. So as an example, if I have C3H8, this is your propane molecule, apologies. So then if I want to know, like, what's the complete combustion, I just substitute these values into the formula. So I get C3H8, I'm just substituting x and y, plus, well, x is 3, 8 over 4 is 2, so it's just 2 oxygens. Gives me x is 3 again, so 3 CO2, plus 8 over 2 is 4 H2O. And then if we simplify this, C3H8 plus 5O2 gives me 3 CO2 plus 4 H2O. Now, you may realize that this is very similar to what you've done in O-levels. There are certainly O-level questions that you have attempted, which go balanced equation for the complete combustion of C3H8. And you need to kind of figure it out yourself. But the nice thing about having this general relation is that you don't need to figure it out by yourself, because the general relation has figured it out for you. All you need to do is just substitute x and y, and then you're done. So that's basically it for this video. Hope you've gotten something useful out of it. Thank you.